The topic of this problem is mesh analysis, and we're working with circuits with dependent voltage sources and also independent voltage sources in them. So we're going to work on a problem where we need to determine V sub out, which is the voltage drop across a 2 kilo ohm load resistor on the right-hand side of the circuit. We see that we have a current-controlled voltage source as our dependent source. And the current that controls this voltage source is the current that flows down through the 2 kilo ohm resistor on the right-hand side of the circuit. So that current controls the voltage level at the left-hand side of the circuit. So what we want to do is we want to use mesh analysis to solve this problem. So we immediately know that we're going to be using Kirchhoff's voltage law to solve the problem. We also know that when we're doing mesh analysis, the first thing we do is we assign meshes and then mesh currents associated with those meshes so that we can then sum up the voltages around the meshes to create equations that can be solved simultaneously to determine the mesh currents. So we're going to start with assigning our meshes. Our first mesh we're going to assign in a clockwise fashion on the left-hand side, and we're going to call the current through it I sub 1. And you might imagine the next mesh is going to be on the right side of our circuit, and it's going to have a mesh current I sub 2. We immediately notice that I2 is equal to I sub x because it's the current flowing down through the 2 kilo ohm resistor. So we can write that down to help us out. Because I sub x introduces a third unknown variable. We have an unknown current I sub 1, we have an unknown current I sub 2, and we have an unknown current I sub x. But this is our first equation, which is independent of our other equations. It's a constraining equation that relates I1, I2, and Ix. So let's write the equation around loop 1 as our first mesh equation. Starting at the lower left-hand corner, we encounter the negative polarity of the dependent voltage source. So we're going to write that as a minus 2000 I sub x voltage drop as our first voltage drop as we travel around this loop 1. The second one is the voltage drop across the 2 kilo ohm resistor. That's 2K times I sub 1. The only current flowing through the 2 kilo ohm resistor at the top left is the I sub 1 current. Then we get to the 4 kilo ohm resistor, which is shared between mesh 1 and mesh 2. And so the voltage drop here is going to be 4K and traveling clockwise around this loop, same direction as I1. The voltage drop is going to be 4K I1 minus I2 because I2 is flowing through the 4 kilo ohm in the opposite direction as I1. And then we continue back to our starting point, and that is our sum of the voltages around that closed loop. Our next loop is loop 2. And again, we have three unknowns. We have I sub x, we have I2, and we have I1. That's our three unknowns in our equations that we're going to come up with. So if we come up with a third equation, then we can solve for I1, I2, and I3 using various techniques for solving equations simultaneously. So let's add up our voltage drops around loop 2, starting in the lower left-hand corner, first encountering the 4K resistor. We know the voltage drop there is 4K. We're going clockwise around loop 2, I2 minus I1. And keep in mind that 4K I2 minus I1 is equal to, let me write it up here, 4K I2 minus I1 is equal to minus 4K I1 minus I2, where this 4K I1 minus I2 was a voltage drop that we assigned from our first loop across that. And if we're coming up through the negative of this, then some people might look at this problem and say, well, we should take the negative of the voltage drop that we've already assigned in loop 1 as we sum up these voltages. And in fact, that's what we did. Here is the negative of that voltage, and it's this, which is what we have in our equation 2. So it is exactly what we thought it was. So we continue around this loop, and we run into a 6-volt source, the negative polarity first, so it's minus 6 volts. And continuing around, we have a 2 kilo ohm resistor with I2 dropped across it. So it's 2K So it's 2K I sub 2. And we continue around to the start of that loop, and so our sum is equal to 0. So there's our 3 equations and our 3 unknowns. What we're interested in this problem is V out, the output voltage across the 2 kilo ohm resistor. We know that V out is equal to 2K times I sub 2. If you use the passive sign convention, I2 is flowing clockwise around this loop, then we would assign a voltage drop across the 2K resistor as so, and that is the same voltage as we are measuring, which is V out. So V out is equal to 2K I2. And so what we really need from these set of 3 equations and 3 unknowns is we need I2. And so if we use those equations and we solve them simultaneously for I sub 2, we get an I sub 2 equal to 3 milliamps. Once we have I sub 2, we can come down and use our equation for V out, and we end up with a V out equal to 6 volts.